In this series of videos, we'll return to mechanics, that is to say motion, forces, energy, but we'll look at it in a new way under the context of simple harmonic motion. And simple harmonic motion is a form of oscillation, oscillation being a back and forth motion around an equilibrium position. Now, oscillation is actually a general term. It's a little more general than simple harmonic motion, or that is to say, simple harmonic motion is a subcategory of oscillation. Oscillation could be any object that moves back and forth around an equilibrium position. The difference with simple harmonic motion is that it will make a regular, repeatable, and more importantly, a predictable motion, as opposed to the general oscillations where it may be very unpredictable. It repeats, but it's not doing it in a predictable or repeatable manner. So just to give you some examples of different objects that may be oscillating. Starting with irregular objects, the wind would be a great example of objects that oscillate in an irregular way. So for example, you might imagine a leaf, and the leaf, when the wind blows, that leaf may blow back and forth, but again, in a very irregular way. Another really great example of an irregular would be a flag. So as the flags blow back and forth in the wind, there is an equilibrium position, a position where the flag would normally be, and the flag goes back and forth, but it doesn't do so in a regular or in a repeating manner. Another example, which I don't have listed on here, would be earthquakes. Earthquakes are a form of oscillation, a form of back and forth motion, but very rarely do they follow any kind of regular or repeated pattern. It's a little bit more irregular, the jerky motion that they follow. So we won't really focus very much on these, but you certainly should understand the difference between just general oscillatory motion and simple harmonic motion, which is a little bit more specific. The following examples that I'm giving you are more in the class of the simple harmonic oscillators. That is to say that they repeat themselves in a little bit more regular pattern. If you can imagine for water, for example, if you drop something in the water, what that object does is it pushes down the water and creates a depression in the water. Now the water is not going to stay like that because the forces that are set up by that motion are going to push the water back up, and the water is beginning to move, but when it reaches the equilibrium position, it's going to have enough momentum to overshoot that equilibrium position, and then it will go up to a high position like this, as I'm sure you've all seen water when you drop something oscillating up and back and forth, up and down. If you could see a small leaf or there was an animal like a duck, and it was at that point in the water where the object had been dropped, then that object would begin to oscillate back and forth around the natural equilibrium position, that natural equilibrium position being the normal calm level of the water. Strings under tension is another great example, and it looks very similar to this. If you pull a string that's under a significant amount of tension, like a guitar string, so if we were to pull the string upward and then allow that string to go, it would follow a similar motion. The string would begin to oscillate back and forth around that natural equilibrium position. Right, so equilibrium position we'll mark on here. The string begins to oscillate around that natural equilibrium position, and obviously this is very important. All stringed instruments are essentially examples of simple harmonic oscillators. In fact, it's a more general rule, almost all musical instruments are examples of simple harmonic oscillators. The nice thing about the strings is that they're one of the simpler ones. It's a little bit easier to see that simple harmonic motion. Many of the others, it's not as easy to see the simple harmonic motion, even though it is actually there. If you can imagine an object rolling around in a perfectly circular bowl, or a half circular bowl, semicircle, so if we were to take a marble and pull it up to the top, then what you would see is that the marble would begin to move back and forth around an equilibrium position. The marble would hit the equilibrium position where it would naturally like to be, which is at the bottom of the bowl, and then overshoot and come back up. And the marble will simply roll back and forth following a regular and repeatable pattern of simple harmonic motion. Objects connected to a spring would be another example. So if you imagine a spring, and we, for example, were to pull on that spring, what would happen is the spring would stretch, and when we release this, the spring would pull the object backwards, it would reach its equilibrium position right here, and then it would overshoot that position, causing the spring to become compressed, and as the spring becomes compressed, it would begin to push in the opposite direction. And so again, we have that natural equilibrium position. That natural equilibrium position, and the spring will begin to cause the mass, not the spring, but the mass, to begin to oscillate back and forth across that equilibrium position. Another great example, and probably one of the most popular ones, this is obviously a very instrumental piece in some of the early clocks, and that is the pendulum. The pendulum is a pretty simple device, just simply some form of mass, typically spherical or circular, something that has a very small profile that won't be affected by the wind. And when the pendulum is pulled off to one side and released, it begins to oscillate back and forth around that natural equilibrium position, which would be sitting straight down at the bottom. So these are all examples of oscillation. And what we need to do now, before we go too deeply into the topic, is we're going to set up some of the basic aspects of simple harmonic motion by defining some of the terms that you're going to see commonly in them. And obviously, one of the terms that you would think would be very important about predictable motion is the time that it takes for that object to make motion. So there is a special name for this period of time. I mean, of course, you can simply measure time. But when we talk about the time for the object to complete one full cycle of its motion, we give a special name for that, and that is called the period. So in the case of the pendulum will swing over to one side and then swing back over. So one full motion is over and all the way back. Now at that point, it will begin to repeat the cycle over and back, over and back. So each time it does that, that's one full motion. And that period of time that corresponds to that is called the period of its motion. It's given the symbol capital T rather than little t being a general time, just any random time, and T being a specific time that is characteristic of that particular oscillator, whether it be a string or a marble in a bowl or a mass on a spring. It's a characteristic time for that particular object. Now, what causes the object to make this back and forth motion? Obviously, there must be forces that are acting on this object. And the name for this, and the reason why objects undergo simple harmonic motion, is because of a property called the restoring force. Now, in a simple sense, the restoring force is the force that points back towards the equilibrium position that only occurs in a situation of stable equilibrium. And I'll show you what I mean by that in just a second. But for example, if we displace an object, we give it a change in x in the positive direction upward. What a restoring force means, the restoring force points towards the equilibrium position. So if we pull the oscillator in the upward direction, that means that the restoring force is going to point in the downward direction. If, for example, we have an object which is displaced out to the right, then we would have a restoring force must be a force which points to the left. Let's go back and look at a couple of the pictures. I pull this pendulum out to the right. The tension points up and to the left. That means that the tension has a component which is towards the equilibrium position. Now, weight is also there, but realize that the weight points upward. So the weight can't pull it back towards the equilibrium position. It's the tension that pulls it back towards the equilibrium position because there is a small component that points in that direction. That's the restoring force. If we look at the marble in the bowl, when the marble's at the bottom, the force points directly upward and the marble is in equilibrium. But as the marble moves out to the side, the normal force begins to point inward. Well, always points inward in this, but in this case points in the direction that is towards the equilibrium position. That is to say that there is a small component of the normal force that points in the direction of the equilibrium position. In the case of the spring, it should be pretty obvious. If you pull the spring outward, the spring immediately begins to pull the object backwards. If you compress the spring, then the spring begins to push in the opposite direction. So when the spring is compressed on this side, it pushes the mass back to the right. And when the spring, I should say, is stretched, then it pulls back on the mass and brings it back towards the equilibrium position. Same thing with the string. We pull it up, the tension in the string pulls the string back down always pulling it towards the equilibrium position. That's what we would call a restoring force. So in the case of the marble in a bowl like this, notice that the restoring force always points back towards equilibrium. That's called a stable equilibrium. An unstable equilibrium would be one that looks like this, in which we put a marble, away from the equilibrium position, which is right here, and in this case the marble is going to just move farther away. It's not a restoring force. It's actually going to move the marble away from the equilibrium position instead of towards the equilibrium position. But in simple harmonic motion, we'll always be looking at that sort of restoring force that naturally wants to bring the object back towards its equilibrium position. So let's actually define what the term simple harmonic motion means. We're going to kind of build this definition, or this defining term for simple harmonic motion. The definition of simple harmonic motion is actually in the form of an equation, and that is that when an object is disturbed from its fixed equilibrium position, the bottom of the pendulum, the bottom of the bowl, the place where the spring is not compressed or stretched, the natural place for the string. So when it's displaced from that, when it experiences an acceleration that is proportional and opposite to the direction that you've displaced it. You pull it to the right, then it feels an acceleration that is proportional to how far you've pulled it, but in the opposite direction. So if you're thinking about that in terms of an equation, that is A is proportional to, not equal to, proportional to minus delta x. And obviously, since we know that F equals ma, the reason why the A is proportional to delta x is because F and A are also proportional to each other. So when you pull a spring in one direction, then a force arises, and that force is proportional to the displacement, how far you pull it. The farther you pull it, the greater the force. I think that's pretty clear. And therefore the acceleration that the object experiences is also proportional to how far you pull it. So that's helpful, but you couldn't solve a problem from it. You could just simply set up that if, for example, you doubled the displacement, then that would therefore double the acceleration that the object feels. But ultimately what we would like to do is to bring this to an equation, and since there is a simple proportion between these two, it's almost in the form of y equals mx plus b. But in this case, we won't need to worry about the b. It's simply going to be y equals mx, where y is the acceleration and x is the same as the x over here. It's the displacement, and in this case it's the independent variable. So what we're missing is the m. And in this case, in order to turn this into an equation, what we need is some constant times x. Now, right now we're not going to replace c with the property that has its true name. But what I do want to do is to at least look at what are the units for this constant c. So big C is a constant, and it's pretty easy to figure out what the units are for it because we can just look at this equation, A equals minus CX. Again, remember the minus comes from the fact that the restoring force always points in the opposite direction as the displacement, therefore the acceleration always points in the opposite direction. And we can take the equation A equals minus CX, that's meters per second squared, and that must be equal to some constant. I'm going to leave out the negative for right now because the negative has nothing to do with the units. And the displacement then would be in meters. Well, you can see that these meters will cancel those meters, and therefore the units for C are inverse seconds squared. Inverse seconds squared. And in the next part, we'll take this formula just a little bit further, and we'll see that this c is not only is a constant that's part of the simple harmonic motion formula or equation, but it actually is related to another property of the simple harmonic motion that's going to allow us to have a little more specific formula, one that's a little more useful for solving problems that involve simple harmonic oscillators.